Imagine, just for a second, that you're standing in a perfectly dark room, watching two shadows converge on a wall.
Okay, I can picture that.
Right, so as the light source behind whatever is casting those shadows moves, the shadows, they get closer and closer together.
Yeah, that makes sense.
But right before they actually touch, something completely bizarre happens. The closer they get to each other, the faster they merge.
Oh, wow.
Yeah. In fact, in that split second right before they become one, the edges of those shadows are actually moving across the wall faster than the object casting them, faster, mathematically speaking, than the speed of light.
It's totally counterintuitive.
Yeah.
It forces your brain to complete double take.
It really does. Welcome to the Deep Dive Lab, everyone. Today, we aren't just talking about shadows on a wall. We are doing a deep dive into literal blind spots in light itself.
Yeah, these points of absolute nothingness that are actually breaking the cosmic speed limit right before they vanish.
Exactly. So let's unpack this. Why does a point of nothingness suddenly accelerate past the speed of light? And how did an international team of scientists just catch this impossible ghost on camera?
Well, to understand what this team captured, we have to look at complex wave systems. I mean, when you have multiple waves of light bouncing around and crashing together, they interfere with one another.
Right, like ripples in a pond intersecting.
Exactly like that. And in certain exact microscopic coordinates, a peak of one wave perfectly meets a valley of another. They completely cancel each other out.
So that's destructive interference, right? At that specific point, the intensity of the light is just zero. There is absolutely no light there.
Spot on. And because there is no light, the phase, the way its rhythm or its timing basically becomes completely undefined. I mean, you can't measure the timing of a wave that doesn't exist.
That makes sense.
Yeah, and that exact coordinate of zero amplitude and undefined phase is what we call an optical phase singularity.
I picture it a lot like the eye of a hurricane. If you're standing in the eye wall, the wind is screaming past you, wrapping around in a very clear, measurable direction.
Right, a massive amount of energy.
But if you step into the exact dead center of the hurricane, the wind speed drops to zero. If someone asks you, which way is the wind blowing right here, the question itself loses meaning. There is no direction because there is no wind.
That structural similarity is actually exactly why scientists have historically referred to these as light hurricanes.
Yeah.
The phase of the light actually winds around these dark points.
Oh, really? That's what they call them.
Yeah. And because of that winding, these singularities carry what physicists call a topological charge. Depending on which way the light winds, clockwise or counterclockwise, they get assigned a charge of +1 or -1.
So they essentially have a spin, like magnetic poles. And I know that for a very long time, the standard model treated these singularities exactly like interacting particles in a liquid.
Right. A positive charge and a negative charge attract each other. When a +1 singularity meets a -1 singularity, they annihilate. They just pop out of existence.
Okay, so if the model works perfectly, if they just act like positive and negative particles, where does the physics break down? Why is there a mystery here?
Well, the breakdown happens in the math of random wave interference. The theoretical models predicted that right before a singularity and an anti-singularity annihilate, their space-time trajectories have to form a continuous, closed curve.
Okay, a closed curve.
Yeah, and to make that mathematical curve close smoothly, their velocities have to skyrocket. Right at the moment of collision, they should accelerate infinitely.
Infinitely, meaning the math was telling physicists these points of nothingness were blowing right past the speed of light.
Precisely. They reach what are called formally divergent velocities. But here is the massive wall researchers hit. Actually measuring this was physically impossible.
Because it's happening too fast.
Way too fast. We are talking about events that happen in femtoseconds. A femtosecond is 1/4 of a second.
That is just, I can't even wrap my head around that. And not only are they blindingly fast, but they are happening at a spatial scale vastly smaller than a single wavelength of light. Right?
Exactly. You can't just point a standard lab microscope at this. The older generation of electron microscopes were simply too blurry and, well, too slow to catch the final crash.
It's like trying to photograph the impact of a speeding bullet using a camera from the 1800s. You just get a smear of exposure.
That's a perfect analogy, which is why the theory of superluminal speeds remained just that theory. Scientists were literally left in the dark about the exact dynamics of these annihilations.
But that changed with a massive breakthrough just published in the journal Nature. Here's where it gets really interesting.
Oh yeah, the methodology here is incredible.
Right. This research was led by Dr. T. Butcher, Dr. A. Gorluck, corresponding author Dr. I. Kummener, and an international team spanning the Technion Israel Institute of Technology, Harvard, Stanford, MIT, and others.
A real all-star team.
Seriously. And they didn't just tweak a microscope, they built a completely new way to see the microscopic world by combining an ultra-fast transmission electron microscope, a UTEM, with a technique called free electron Ramsey imaging, or FAIR-AI.
The engineering behind this is just a marvel. They aren't just taking pictures with light, they are firing a femtosecond laser pulse to create the complex light field.
Okay.
And then they fire a single highly controlled electron directly through that field.
So they're using the electron as a physical probe to essentially feel the shape of the light.
Exactly. As the electron passes through the light wave, it interacts with the optical field. It exchanges energy with the light, absorbing or emitting photons.
Oh, wow.
Yeah, and by measuring the exact energy spectrum of that single electron after it passes through, the researchers can mathematically reconstruct both the amplitude and the phase of the optical field it just served through.
Yeah. And the resolution they achieved with this is staggering. Because they're timing these electron pulses with such precision, they captured frames every 3 femtoseconds? That's deep subcycle temporal resolution.
Right. They're taking multiple distinct pictures within the time it takes a single wave of light to oscillate just once.
Which is wild. And spatially, they reached a resolution of 20 nanometers, which is about 350 times smaller than the wavelength of the infrared light they were using.
Now, they essentially mapped the exact phase of an optical field at a scale no human had ever reached before.
But the camera alone wouldn't have been enough, right? The other half of this breakthrough is the environment they created to actually observe the singularities.
Exactly. They didn't just flash a laser in a vacuum. They used a tiny, super pure flake of a material called hexagonal boron nitride, or HBN.
Which is where things get heavily quantum. Inside this incredibly thin HBN membrane, the light pulse creates hyperbolic phonon polaritons, or PHPs.
Yeah, it's not just pure light traveling through space anymore. The light wave hits the crystal lattice of the boron nitride, and the atoms of the crystal start vibrating in sync with the light.
So it's like a hybrid wave of light and matter.
Right, and that hybridization is crucial because of the material's dispersion properties. Hexagonal boron nitride is highly anisotropic.
Meaning it responds differently depending on the direction the wave is moving.
Precisely. When the light couples with the vibrating atoms to form these polaritons, the group velocity of the wave, the speed at which the overall wave packet moves, slows down drastically. It can be up to 100 times slower than the speed of light in a vacuum.
So it basically acts like thick molasses. It creates an ultra-slow motion racetrack where the wave packet survives for over a picosecond, which, in the quantum realm is an absolute eternity.
An absolute eternity, yeah.
But slowing the wave packet down introduces another mechanical quirk, right? The source material mentions this expands the variance of the wave vector distribution. Hold on, what does that actually mean for the physical space of the wave?
Okay, so think of it like this. Are we saying the internal ripples of the wave are getting squished and skewed so tightly that the blind spots between them are forced into more extreme, violent collisions?
Yeah, exactly. Is that what's happening?
That is exactly what is happening.
Oh, yeah.
The overall packet is moving like molasses, but the internal phase velocities are running wild. The wave vectors, the arrows pointing in the direction the phase is moving, are forced into vastly different directions and magnitudes.
So it just creates total chaos.
Complete chaos. This massive variance creates a highly dense, chaotic phase landscape where singularities are constantly being born, attracting, and annihilating in incredibly tight proximity.
Which brings us to the actual discovery, and the numbers here are just jaw-dropping.
They really are.
We know from the math that in a normal free space vacuum, you would expect only about 0.4% of these singularities to break the speed of light right before annihilation. Almost zero.
Right, a tiny fraction.
But because the researchers used this HBN material to slow the group velocity and wildly squish the variance, the numbers completely shifted. In this experiment, a staggering 29% of the singularities exceeded the speed of light.
Yeah, coming 9%. And the average velocity of the entire ensemble of singularities they tracked was 1.04 times the speed of light.
That is insane. They literally caught them on camera doing this. They mapped the exact moment the positive and negative charges swirled toward each other, accelerated, and crossed that cosmic speed limit.
They did. But, what's fascinating here is the physical implication.
Well, wait, hold on. This is the ultimate intellectual pushback. We all learn in basic physics that Einstein proved absolutely nothing goes faster than the speed of light. See, that is the hard limit of the universe.
Right, Einstein's famous speed limit.
So how does a finding like this, published in Nature, not completely shatter the fundamental laws of physics?
It's a great question. It comes down to distinguishing between a physical object and a kinematic effect.
Yeah.
You have to remember what a singularity actually is. It is a point of zero amplitude. It is literally a coordinate of nothingness.
Right. The eye of the hurricane?
Yes. And because it is nothing, a phase singularity does not carry energy. It does not carry information. Therefore, it is entirely exempt from Einstein's speed limit, which specifically dictates that energy and information cannot travel faster than c.
Ah.
Okay. So the apparent superluminal motion of the singularity isn't a physical object moving through space. It is just a kinematic trick of how the phase landscape of the wave is evolving in space and time. It doesn't break causality at all.
Ah. It's like standing on Earth and sweeping a massively powerful laser pointer across the surface of the moon.
Oh, I love that analogy.
Right. Like, if you flick your wrist fast enough, the red dot of the laser might move from one crater to another across the moon's surface faster than the speed of light. But no actual physical particle and no piece of data traveled from crater A to crater B that fast.
Exactly. The dot itself isn't a physical thing moving laterally. It's just a geometric intersection of the light hitting the surface sequentially. The particle analogy for these singularities just totally breaks down.
It perfectly captures it. The dot is an intersection, not an object.
Yep. And this realization, seeing it proven experimentally, is what finally shatters that old particle singularity analogy. For decades, physicists said, look, their distance correlations behave exactly like interacting particles in a liquid.
But they don't, do they?
Not at the extremes. When the team mapped these velocity distributions, they saw a massive, heavy tail of extreme superluminal speeds.
Meaning the graph of their speeds didn't drop off neatly like physical particles would. It stretched way out into the faster-than-light territory.
Exactly. Particles of matter with mass cannot have a heavy-tailed velocity distribution that pushes past c. The singularities are fundamentally wave-borne phenomena, entirely dictated by phase gradients, not physical mass.
Okay, so now that we know these light voids break the particle analogy and the ultimate speed limit, how does this actually change our world?
Well, if we connect this to the bigger picture, it has massive implications. Let's start with microscopes.
Yeah, the source material talks about these singularities inherently creating something called super oscillations. What is that?
Super oscillations are a fascinating frontier. A super oscillation occurs when the local field phase gradients of a wave change faster than the wave's own maximum spatial frequency limit.
Okay, meaning the light wave wiggles much, much tighter and faster than its own wavelength technically dictates it should be allowed to.
Yes. And because this experiment proves that the chaotic birth and death of singularities are constantly creating these extreme super oscillations, it could completely revolutionize super-resolution imaging.
So we could see things we previously couldn't.
Exactly. We are usually limited by the diffraction limit of light. We can't easily see things smaller than the wavelength of the light we use to look at them. But if we can harness these super oscillating phase gradients, we could use light to clearly resolve viruses, or even complex atomic structures, far smaller than the natural wavelength of the light itself. It essentially hacks the resolution barrier.
Wow. And it doesn't just improve optical microscopes, right? It actually solves a massive headache for electron microscopes, too. There's this phenomenon called the bee swarm effect.
Oh, yes. The bee swarm effect has been the bane of material scientists for years.
Because anyone who has looked at ultra-high-resolution electron microscopy knows that when you push the machine to its absolute limit to see atoms, the image is often covered in this weird, grainy, fluctuating fuzz.
Right, and the standard assumption was that this fuzz was just inherent, chaotic noise, unavoidable random thermal fluctuations in the electron beam itself.
What this research implies, it's not random at all. That fuzz limiting our view of the atomic world is actually the chaotic birth and death, the superluminal acceleration and annihilation of these exact phase singularities occurring within the electron wave itself.
That is the big revelation. Now that we understand the heavy-tailed velocity distribution and the exact phase-space correlations of these singularities, Engineers don't have to treat the bee swarm as random noise anymore.
They can predict it.
They can model the dynamics of these deep subwavelength events at an ensemble level. By understanding the math of the singularities, they can devise algorithms or hardware filters to mitigate the noise.
So they can literally wipe the fuzz away and push atomic scale imaging to unprecedented levels of absolute clarity.
Exactly. It's a massive leap from material science and medicine. But there's a computing angle here too, specifically regarding quantum computing and skyrmions.
Right, skyrmions. Remember how we discussed that these singularities have a topological charge, a plus or minus one spin based on how the phase winds around them?
Yeah, the light hurricane effect.
Because they hold that topological charge so robustly, researchers are looking at the possibility of mapping quantum information onto multidimensional topological structures called skyrmions.
A skyrmion being essentially a complex, microscopic whirlpool of phase that is stable enough to act as a data bit.
Precisely. Tracking the ultrafast dynamics of these complex singularities allows us to understand how to create, manipulate, and annihilate these phase whirlpools on demand.
And because they can exist at such unimaginably small scales and operate at femtosecond speeds, they really pave the way for encoding massive amounts of classical and quantum information. We are looking at the foundational architecture for ultra-dense, light-speed quantum computing.
So what does this all mean? Let's recap the incredible journey this deep dive has taken us on. First, scientists managed to build a camera system using an ultra-fast electron beam to physically probe a light field fast enough to actually film the fleeting life and death of light singularities.
A monumental achievement on its own.
Truly. Second, by watching them on a slow-motion track made of boron nitride, they caught these points of nothingness accelerating past the speed of light right before they merged.
The 29% that broke the limit?
Yep. And third, by doing the math on those superluminal speeds, they proved that while light singularities might act like liquid particles most of the time, that comforting analogy completely shatters at the extreme limits of nature.
And this raises an important question, really, about how human understanding progresses. We rely so heavily on analogies like, singularities are just particles, because they make impossibly complex quantum systems manageable for our brains.
We need them to make sense of the world.
Right. But the true beauty of science lies in finding the exact edges where those reliable analogies finally break down. It's precisely in the breaking of the rules, in the discovery of things like heavy-tailed velocity distributions of nothingness, that we find the next fundamental layer of truth about reality.
It makes you wonder, if a literal point of nothingness can travel faster than light, carry no energy, yet hold the key to the next generation of quantum computers and supermicroscopes, what other blind spots in nature are hiding the greatest leaps in human technology, just waiting for a camera fast enough to see them?
It's a thrilling thought.
It really is. Thank you for joining us in the Deep Dive Lab today. We hope you enjoyed this exploration of the invisible, superluminal world. Please follow and subscribe for more incredible stories from the very frontiers of science. Until next time.